They built it to last 100 years. It lasted 4 months. When the Tacoma Narrows Bridge opened on July 1, 1940, it was a marvel. Stretching 5,939 feet across Puget Sound in Washington state, it was the third longest suspension bridge in the world. Engineers were proud, the public was awed, but almost immediately, something felt wrong. The bridge moved, not in the way structures are supposed to subtly flex, but visibly, dramatically, in long rolling waves that traveled down the deck like something alive. Drivers reported watching the car ahead of them disappear into a trough, then reappear as the road crested back up. Workers started calling it Galloping Gertie. Some people drove out just to feel it, a strange, nauseating thrill. A few loved it. Most didn't cross twice. Engineers weren't blind to the problem. Stiffening measures were discussed. Studies were ordered. But the bridge kept standing day after day, and urgency faded. It had been built. It was open. Surely it would be fine. It would not be fine. November 7, 1940. Wind speed 42 miles per hour, not a record, not even close to a record. What made that morning different wasn't the strength of the wind. It was its rhythm. Every physical object has a natural frequency, the rate at which it wants to vibrate if you disturb it. Tap a wine glass and it rings at one specific pitch. That's its natural frequency. The Tacoma Narrows Bridge had one too. On November 7th, the wind wasn't just pushing the bridge. It was creating repeating vortices, little swirling pockets of air that peeled off the underside of the bridge's solid plate girders at almost exactly the bridge's natural frequency. This is called resonance. Think of it like pushing someone on a swing. If you push at random, nothing much happens. But if you push at exactly the right moment, every time, small pushes stack up into enormous motion. That's what the wind was doing. Accidentally, precisely, catastrophically. The oscillations grew. The twisting began. By 10 a.m., the bridge was rotating 45 degrees side to side, one lane sitting nearly vertical while the other dropped away below it. Professor F.B. Farquharson, an engineer who had been studying the bridge's motion for months, was there that morning. He tried to rescue a dog trapped in an abandoned car on the deck. The dog, terrified, bit him. Farquharson retreated. The dog did not survive. Farquharson himself barely made it off. He described the walk back to the tower as crawling, the deck tilting so severely he couldn't stand. At 11:02 a.m., a 600-foot section of the main span tore free and fell 190 feet into Puget Sound. The rest followed in pieces over the next hour. The water was shallow enough that chunks of concrete came to rest just below the surface, visible from above like a grave marker. The only fatality was that dog. But the collapse rewrote engineering. Aerodynamic forces, wind behavior, resonance, flutter became central to every bridge design that followed. The solid plate girders that had caused the vortex shedding were replaced in every future design with open truss systems that let wind pass through rather than build beneath. They studied the wreck. They ran the numbers. They built better bridges. They never made this mistake again. But they made new ones.